Welcome to the BS and Beer Show. BS stands for Building Science, of course. Our topic tonight is unvented roofs and fluffy insulation, and we will get into exactly what that means. My name is Mike, and we do a thing here of presenting our beverages. I am drinking a kombucha. It's not homemade, it's gingerberry kombucha, very good stuff. I'd like to thank everybody in the audience for coming tonight and anybody who's watching this in the future. Really like to thank our guests, Bill and Koda, for joining us. We've been doing this BS and Beers for a few years now, but only been doing them via Zoom here for a couple of months, and it's really exciting. It's great to have this national platform, but it originally started and we really encourage local groups. So if you want to start your own local BS and Beer group, feel free to use the name or any version of it via Zoom or in person. It's just great to get people together at a local pub or place of business and talk about building science. I'd also like to thank Green Building Advisor and Fine Home Building Magazine for being our media partners. And a video of tonight's conversation will be available at Green Building Advisor and also on our new website, thebsandbeershow.com, which was put together by Bob Swinburne. Finally, I'd like to introduce the other hosts, Emily, Travis, and Justin, and I will turn it over to Justin.
Hi guys, Justin Fink from Fine Home Building and Green Building Advisor. Tonight I am drinking my usual New England Brewing Company Sea Hag. I don't know what this big kombucha trend is on BS and Beer lately, but it's BS and Beer, not BS and kombucha. So I'm just trying to keep it real over here. A couple of things, just a little housekeeping stuff before we get going. Down at the bottom of your screen, for anybody who's new to Zoom, you're going to be able to click on the chat box. The chat box is where you're going to be able to communicate with us as we're giving presentations. I will be watching the chat box so that as you guys have questions, I can feed them to the presenters, and we can you can also have just a conversation in the chat box with everyone else in the audience. The key here is there's a drop-down menu in the chat box. You have to click it to where it says all panelists and attendees. Otherwise, your notes will only be coming to us and no one else will see them. The other thing to know is that we are going to, one more thing is we had some questions last week, some confusion over speaker view versus gallery view. For anybody who's new to Zoom, you have two options of what you see on the screen. One, you'll see only the person talking, and when the person talking switches a lot, it gets to be kind of chaotic. Or you can click on gallery view, and you can see everyone who's kind of a presenter or host all at one time. So I recommend gallery view. We're going to be doing this in 3 portions tonight. The first segment is going to be the guest presentations by Koda and Bill. Then the middle section, we're going to be answering questions from the audience, and I guess that mostly Koda and Bill will be answering those questions. And then the third segment, we call it kind of free form. We're just going to see what else we want to do. We're going to see where the conversation goes and what we want to do with it. We are going to end by 7:30. If you come in late or you have to leave early, like Mike said, this is going to be available after the fact. Go on to YouTube, go on to greenbuildingadvisor.com, and you can watch a recording of it. So with that, I will hand it over to Emily.
Hey guys, Emily Mottram. And you're wrong, not about kombucha, but Mason Lord every week with the bourbon. So it's BS and bourbon tonight, Mason. Eagle Rare. So it's going to be BS and anything that starts with B. I have the pleasure tonight of introducing our guests. So tonight we have Koda and Bill. Koda works for Building Science Corporation. He performs forensic field investigations and building failures. He's also done consulting work for new and retrofit construction and design and building enclosure and mechanical systems. Koda has conducted extensive research and field work in building science topics, so we're really excited to have him on tonight to talk about unvented roof assemblies and fluffy insulation. Welcome, Koda. And Bill has 25 years of experience working in weatherization and energy efficiency programs. Probably have taken one of your programs over the years. He's trained and provided technical assistance in dense packed cellulose and super insulation for net zero buildings. Currently, he works with the cellulose manufacturer NatureTech, and they are bringing the first truly de-dusted cellulose insulation to the marketplace. So I would like to hear more about that. So welcome, Bill. So Tonight we have Bill and Koda, and I will kick it off with Travis. Give us a little toast and introduce yourself.
Hello, hello. I am Travis Brungart. I operate Catalyst Construction in Kansas City with my partner Joe, and along with another friend who's also named Joe. We run the KCBS and Beer discussion group. So it's nice to have everyone here tonight. I do like to kick the show off with a toast, but first I have to introduce my beer. Tonight I am the lucky recipient of one gift beer from Dan Edelman, who runs the Jew Brew Funky Farm Brewery. This is Phenomenology, and it lives up to its name. It's pretty tasty. It's a sour. I like the sours, so I'm about that life. So I do want to propose a toast, though. So raise up your glasses. May your risk always be low, your performance be high, and your assemblies be durable.
Cheers.
Cheers.
On to the business at hand. I would like to just briefly have our guests say a little something about themselves, anything they want to add about themselves or their businesses. And of course, you got to introduce your drinks, gentlemen. But I also wanted to ask, and I'll start with you, Bill, if you could, just what does an unvented roof mean, and why would anyone want one? After you introduce your drink, of course.
Yeah, all right. Well, tonight I'm drinking some Maine Root Sarsaparilla in honor of the Maine group. So unvented roof assemblies to me mean a roof assembly that we insulate typically with dense packed cellulose. But to me, it can't be loose and fluffy. If it's loose and fluffy, then it's not going to work. So I'm going to be talking about density and the importance of density, the critical importance of density in these roof assemblies. And that, to me, is the key to making these things work. And we'll talk a little bit about how many were out there and some of the issues we've seen. But, yes.
That helps. Maybe you could inform us a little bit also, Koda. Of course, what are you drinking? And be sure you tell us a little bit more about yourself. But I'm curious if the code approves these just blanket, or is this a deal like Bill says where it has to be at a certain density? Can you talk a little bit about the way the code views unvented assemblies in addition to your drink and yourself?
You bet. So just as a bit of background, Building Science Corporation, for those who don't know, is Joe Stiebrick's company. I've been working for him for about 20 odd years at this point. A lot of my work is going to look at various screwed up buildings of various types, as well as advising other people on how to avoid those pitfalls. On top of that, doing a bunch of research under the Building America program. Next topic, drink. I've not grabbed my beer yet, but I'm going to grab, and when I'm done talking on the first part, I'll grab something from our local brewery, Aeronaut. It's fantastic to have a brewery within staggering distance. And your question on code. The code currently, as it is written, for instance, residential code R806.5 does not permit dense pack as an option on its own. Does not meet code requirements. We looked at this problem, which I'm going to talk about. If somebody else wants to promote a code option, they're welcome to, but it's not going to be coming from us.
Excellent. Well, with that, I'll kick it back to Mike, and we can get into the presentations.
Yes. Let's, we didn't really pick who goes first here, but yeah, maybe we'll start with Bill again, if that's okay. You want to do 5 to 10 minutes, Bill? I'll give you a 5-minute warning, roughly, just to keep you on track.
All right, you're going to share my screen.
Yeah, you at the bottom of your screen, if you hover your mouse at the bottom, there should be a green button that says share screen.
Okay.
If you're on a PC, if you're on a Mac or an iPad, I'm not sure.
Also green on Mac. Still, yeah. It's working. The magic of the internet.
Okay, everything all set?
Yep.
Yeah, looks good.
Okay, a little bit about little bit about my history with unvented roofs. Back in 1992, I started out my career working with a local weatherization program in Albany, New York. That's when we started dense packing roofs. And Jim Fitzgerald at the time was kind of instrumental in promoting this. And we continued to use this technique on multifamily buildings across New York State until about the mid 90s. We dense packed, a couple hundred roofs at that point. But it was during my 9 years of running the weatherization assistance program up in central Vermont, where we dense packed well over 1,500 roofs just in our territory alone. And there are 4 other agencies in the state. So you multiply that number by 5 to kind of come out with a statewide number. Today the weatherization assistance programs, both in Vermont and Maine, continue to use this along with the hundreds of home performance installers. So, all in all, we have tens of thousands of these roof assemblies, that we've done over the years. So this certainly is nothing new. This is not something, experimental. At least I don't consider it in my mind. So here's some pictures of, in weatherization, typically we're dense packing behind tie-par. So this could be a knee wall. This could be, just a regular cathedralized ceiling. Different, a lot of times if there's existing fiberglass in there, we're pulling out the fiberglass before then we're injecting the dense pack. If there's a thin little bed in there, then we will then we will dense pack, basically pushing that fiberglass back to the inside. We'll talk about that a little bit more. And here's some other ones with, insulating some slopes from an attic, and then up on a roof, real low slope roof, basically opening the top of the roof system and injecting the cellulose in that way. So when I started working for National Fiber after working for the weatherization program, was there for 11 years after that. We dense packed, thousands of more unvented roofs across the Northeast. So, and with new construction, a lot of times, or some of these, we were injecting it. We like to inject behind the insulweb fabric because we can see behind it, you can feel the density behind it, and it provides air relief on those. So the key to unvented roof assemblies with cellulose is this: cellulose has to be dense packed. It has to be self-supporting because we have to have that insulation remain in contact with the exterior roof sheathing. When we have separation, that's when we have problems. So that picture on that lower left-hand side is a picture where the ceiling actually has been taken down after it was dense packed, and we can see the insulation remaining in place. If the insulation fell out of the cavity, that would be an indication that the density was not correct. And that insulation, the picture over on the right-hand side, is me pressing against some cellulose that was in a, that is not a dense pack. That was loosely packed in there. That's gonna be, more inclined to have some issues over time. So the density is important because it does a number of things. One is, again, we need that cellulose to be in contact with the roof sheathing. So this is vital because it allows the hygroscopic properties of the cellulose to redistribute that moisture back inward. So, during the winter time, we get outward diffusion of moisture, but the hygroscopic properties actually will now to diffuse that moisture or spread it out inwards. I have some moisture testing data that will show you. So this would be the same in a roof assembly or a big, thick, super insulated wall, where once we stick the moisture probes in there, the moisture readings are consistent from inside all the way out to the outside till we hit that exterior sheathing, showing that it's redistributing it faster than the outward moisture flow. So it's that redistribution that is going to deny the mold and rot causing organisms the quantity of moisture that they need to replicate. The borate-based fire retardants also are antimicrobial. They will assist in that as well, but that's why we don't have things kind of growing in these things. The high density also blocks, the flow of moist interior air leaking through the assemblies. It also eliminates any convective movement. So it allows, some good insulation performance as well as being durable on that. Here's some unvented roof moisture data from a number of unvented roofs, and these range from, looks like 8.5 inches all the way to 18 or 22 inches. Most of these were taken, during March when WUFI is going to predict disastrous things occurring. And we see that during this time, the moisture, maybe about 7, 6 or 7, all the way up to within the cellulose itself to, 10 on the 10% moisture content on the high side. And the exterior sheathing levels there are running between 7 and 13 and a half on those. And I know that 13 and a half one, that building had a particularly wet basement that they were dealing with on that. So again, really, stable moisture contents on those things. So I've seen a handful of roof assembly issues and failures over the years. The first one was during weatherization program. We got a call. We had dense packed the roof. The homeowner said that the ceiling was actually falling down, and that was concerning because, first of all, we had done the work, so we knew that it was done in a good way. So we went out there and discovered that a large branch had broken off the tree and punched a hole through the roof, and then subsequent rainstorms had put enough water in there where it had saturated the cellulose. The next 4 that I became aware of were in the 2000s in my work through with National Fiber. All of those were associated with low density and gaps between the cellulose and the roof sheathing. And 2 of these, unfortunately, resulted in significant damage to the roof sheathing and roof replacement. So again, this is not something you want to go and do if we don't have the ability to do that. So the thought is, if these things just in general don't work, then, as quote John Straub here, where are the bodies? We just don't see this. Again, there are tens of thousands of these things. I've been directly associated with thousands of these things, and we've seen very few. And the ones we did, there were, definitely some installation issues that were involved in that. So here's some pictures of some of you can see this. So this is where I've taken the camera and actually put it up into the cavity. I've dug out the cellulose to allow me to raise the camera up in there, and we can see on the right hand or left hand side the gaps between the top of the cellulose and the roof sheathing. Neither of those were dense packed correctly. The good thing is on both of those, the fix of it, because it had been caught early enough so that there was no damage, is we were able to, in both these, they had fabric that was unsupported. So basically putting up support, strapping the ceiling perpendicular to the rafters, and then reinserting the hose. And that's the one nice thing I like about cellulose is we can now we can increase the density by retubing these assemblies up to where they needed to be. The ones on the right-hand side here, we can start to see, we got some discoloration going on that upper slide there. And on that lower one, we actually see, had gone so far where we started having the cellulose in that case was actually really quite wet on that particular one. Okay, so one way we kind of know that the densities were not correct is we've taken a core sample out of here. I like using a 4-inch pipe to do that. So basically screw it kind of through the cellulose in there, remove all the cellulose from the pipe there, and then we weigh it. If the cellulose is wet or damp, we first dry it out to about 7% moisture content. And then using that formula down below there, we can calculate the density based upon the weight and the overall cavity depth of where it should have been, figure out what the initial density was installed there. Some of the signs for unvented roof problems is if we have insul web up on the ceiling and we see staining on it, or we have a ceiling and notice stains on the ceiling, that would be an indication that we need to start evaluating this. This is particularly noticeable on one of these where we got the call that there's moisture dripping off our unvented roof assembly when the sun shines. Took a little while to kind of figure out what's going on there. So the roof, the sun shines on the roof, forced driving that moisture inward, and it would actually rain inside the attic when that was happening. And again, the density on here. So this was unsupported insul web. So insul web also appears to stretch over time. So that's the other reason why we like to strap it. We can also tell by doing moisture testing into the material. So if we're noticing, if we do moisture test in the cellulose and notice the cellulose moisture content is over 15%, or if we go all the way out to the roof sheathing and notice that it's above 20%, that's an indication that we have issues and we need to resolve there.
Right.
The cellulose, sorry, Mike.
Or just we're kind of at the end of your allotted time. If you can just sort of kick things up a notch for your last few slides.
I'll do
Sorry.
that. So successful unvented roof assemblies, don't install cellulose under roof leaks, address wet basements before you insulate your attic, pull out any existing fiberglass, dense pack behind containment fabric since we can do good quality control behind it. Strap the ceiling perpendicular before or after the fabric is installed. Dense pack to the correct depths for self-supporting densities. Also, I'm a big fan of calculating the number of bags for the ceiling, and so that you know how many bags should go in there. And then we've also gone to pre-filling with a large hole and then finishing up with a smaller hole. Here's the density chart there, just talking about, deeper cavities mean that we have to take longer time to do that. We don't recommend doing these unless you're proficient in achieving consistent densities. Do the bag counts. Manual compression of the fabric allows us to do complete quality control. And remember, any insulation system is prone to failure if you don't do it correctly. Great, thank you.
Excellent. Thanks, Bill. Any quick questions from panelists, or we can go over to Koda?
I actually did have a question, Mike. I get hung up, and I know that this will frustrate you because you've explained it to me before, and Steve Basic will probably bang his hand on the desk in front of him because he's also explained this to me, but I get hung up on the idea of hydric buffering as an advantage in an assembly as opposed to, simply not allowing any moisture in. I wonder, Bill, if you could make it stick for me.
Yeah, so think of a hydric buffer kind of like thermal mass in a house, where thermal mass allows kind of the store and release heat, keeping temperatures inside the house more consistent. The hydric buffering kind of does the same thing in the cellulose. It allows the cellulose to basically take on moisture without then affecting those materials around it. So it acts as a storage for that. And as long as you're not feeding liquid water into the cellulose, we find that, these things don't get out of whack. And again, these moisture tests were taken during early March, when after the winter time, you'd expect, and on the north side of the roofs in many instances, where you'd expect the greatest amount of moisture to be there during the, that time of year.
Fair enough. Thank you.
Yeah.
Bill,
Mike,
if you
do you
could,
want to
Bill, if you could close your screen share.
Okay, great.
Yeah, and let's hear what Koda has to say on unvented roofs and fluffy insulation.
Okay, let me see if I can go ahead and share. Is everybody seeing that so far?
Looks like it is working. And if I remember, I will try to give you a 5-minute warning. But if you're too interesting like Bill was, I may forget. So
No worries. So, what I'm going to be talking about is the research we've been doing on unvented roofs with fibrous insulation. And I'm trying to pack roughly 3 years worth of research into 10 minutes. So I'm going to skip over a lot of stuff here. I'm hoping that enough of this is useful and will come out in context. So, just a bit of background first is if anybody as a designer has a choice, do a vented attic with insulation and a good air seal down at the ceiling line, no mechanicals in the attic, low cost, fantastic durability. It's just a better way to build a roof. That being said, there's a whole lot of cases where folks build up into the roof, or the intrinsic plan of the house is something with insulation and the air barrier at the roof line. So, also by doing that, if you have mechanical systems in the attic, always a dumb idea, it at least contains those mechanical systems inside and recaptures those losses. So this is the current code compliant way of doing it. Yes, spray foam. So you can do that with just straight up spray foam on its own, or the hybrid of spray foam plus fluffy stuff, fibrous insulation, fiberglass, or cellulose. That's not the only way. You can also do it with rigid board on the outside with fluffy stuff inside the cavity. So it's the ratio of these two that's required to be moisture safe. Dense pack insulation, it does not currently meet code. There are a fair number of failures out there. And just as a bit of background, when we see failures, it's specifically up at the ridge. So this is some topic I'll be coming back to. We'll refer to it as ridge rot, but these sloped roof assemblies will tend to collect their moisture up towards the ridge. More on that in a little bit. So let's back up a step and say, why is an unvented roof considered risky? Nobody's going around saying unvented walls are risky. What's the difference going on here? So, it's not just that we've taken a wall and turned it on its side. So the risk that we're talking about specifically here, just to be clear, is that moisture from inside during the winter can get through your interior air barrier, get through the insulation potentially, get to the sheathing, condensation or high moisture content can result. That's the potential failure we're looking at. So there's both air leakage and possibly vapor diffusion as a contributor as well, depending on conditions. One of the fundamental problems is almost all roofing is pretty much a perfect vapor barrier. Felt and asphalt shingles, peel and stick, it's a wrong side vapor barrier in winter in a cold climate. On top of that, there's night sky radiation cooling. The roof will release its heat to the sky and will end up being a fair amount colder than the walls, resulting in more risk of this type of a moisture issue. On top of that, if there are air leaks, warm air rising, stack effect is going to tend to drive air in and upwards into these assemblies. Part of that is that whole ridge rot problem that I talked about. So I'm going to skip over a bunch of stuff. We've been studying this whole problem for a while, going back to, the early 2000s, doing a bunch of test implementations. We found some problems in our test, implementations. So, let's go ahead and skip this part and just talk about I was going to get to this. Okay, so moving on past that Houston research, we did some test implementations in Chicago, cranked up the interior relative humidity in a bunch of side-by-side test roofs. None of these did very well. Admittedly, the cellulose roofs did, substantially better than the fiberglass bat roofs, which were a straight-up disaster. So we said, let's back up a step, do something easier, do some of these in Orlando and Houston, climate zone 2. So we started doing a technique called a diffusion vent. So what am I talking about here? Like I said before, the moisture tends to rise up into the top of the assembly. Would it be possible to release it up at the top? So we covered up the ridge with a super vapor open over 200 perms, but an air barrier closed and water shedding layer, and had that at the ridge, set it up with a ridge vent just to cover it up, and that was intended to release that moisture there. The takeaway from the Houston or Orlando work was that, yeah, that works. That, does provide safety, and a lot more safety than just wrapping the top of it with vapor impermeable peel and stick. So let's jump through these and get over to the actual research that we did. So based on all these things that we learned before, we started to look at things in a cold climate. So we have a test hut that was built in climate zone 5, Westford, Massachusetts, Joe and Betsy's backyard to be technically correct. And we had 8 pairs of north-south roof bays. So you can see that in the stick frame, wireframe model that we had, 4 fiberglass bays, 3 cellulose bays, side-by-side comparisons. Each of them is a north-south pair. And they're separated by guard bays just to keep stuff from communicating side to side. Insulated to roughly oh, sorry, question?
Or no, just we're about halfway through your time. I'm guessing you're probably in good shape.
Yeah, I think we can probably make it.
Yeah, no problem. There's no.
Okay, yeah. Cool. So this is going to be extra complicated. So we had this test hut. We ran it over, multiple winters. Some of the variables we looked at were the vapor retarder on the interior. We had, variable perm vapor retarders, the, certainty membrane, fixed perm, various permeance curves, that diffusion vent either with or without, fiberglass versus cellulose, and lastly, we had a control comparison with that spray foam code compliant roof. We ran it for 3 winters, one under normal conditions, then under elevated humidity, then we actually introduced intentional air leakage into the rafter bays. So this shows that diffusion vent, that strip of vapor open membrane. We also did options called the small and the tight one into various winters, just making it physically smaller or more vapor closed. Just shows it after the instrumentation was done, and then after the interior insulation and vapor control was done. So I'm going to summarize the research findings. There's a whole, multi-100-page paper. So year 1, that was normal conditions, 30–40%-ish relative humidity. The roof with the diffusion vent and the variable perm vapor retarder was consistently the safest. The non-diffusion vents were the worst. The stuff with the peel and stick over the ridge, high moisture contents up into the 20s, 30s, even higher, indications of condensation. We did some calculations of mold based on known standards. It said there shouldn't be any risk, but there was visible settling of insulation. We'll get into that with Bill and discuss that a bit more. Skip that inward vapor drive. So we, given that the non-diffusion vents didn't work very well, we went ahead and replaced them with some other options as more variables. So this was the ridge after winter number 1, a little bit of settling at the fiberglass, and actually a fair chunk more at the cellulose roof. This was actually a chute running down the entire north side that I could run my tape measure down. So we left it in that condition, ran it at 50% relative humidity to kind of push it to the edge of risk. A lot of the assemblies that were pretty much okay in winter 1 actually became substantially worse, lots of really high moisture contents. The mold index we calculated was below 3, but we actually disassembled the ridge and found mold growth. The tight diffusion vent didn't work, but all along during this entire experiment, the spray foam roof is looking at these fibrous insulation roofs with high moisture contents, high humidities, and it's just laughing. It's not seeing any of these problems. The spray foam does do that vapor control that you expect it does. We repacked the insulation after this winter and replaced some sensors. So this just shows some of the damage we saw on the roof. The fiberglass roof had this kind of nasty diaper stain on the netting, and it looked pretty much like there was water at the ridge and just kind of ran down, hit that seam, and kind of condensed down. And we saw little bits and pieces of mold staining. Cellulose roof, I was expecting much less damage, but I was surprised. There were actually, noticeable mold damage, rusty staples, the classic signs of moisture going on up the ridge. That just shows the settling once again, and people would argue like, oh, it's just the netting stretching. The netting dimension was smaller than the amount of belly. I believe that this is the cellulose itself actually being cycled through moisture and then shrinking. It's kind of like shaking the cereal box to get the prize out, same concept. So year number 3, we ran it at 50% humidity once again, added the air leak partway through it. It was a pretty small air leak, about half a CFM per rafter bay. So it's pretty airtight, just a small leak. So one interesting finding before year 2, before air injection, a lot of these roofs behaved a heck of a lot better. Going to Bill's point, a dense pack does make things a lot better. Moisture contents were a lot lower and, pretty much within the safe range. Air injection though, injecting that, we're getting 40% moisture content directly above that leak. However, we disassembled it and we did not see much damage there. So this shows our air injection. You can see the high-tech shop vac that we're using, rotometer flow meter, piped up to every rafter bay, injecting at the bottom of the north side, and it comes out at the top. This shows where we were injecting, and it was pretty much boring sheathing, no visible damage. So we have in my presentation enough graphs to make your eyeballs bleed. So I'm going to just skip to the conclusions and talk about what we'd recommend. So, these unvented fibrous insulation roofs, fiberglass or cellulose, can work, but, the packing matters tremendously and it's still vulnerable to air leaks. We found mold in these assemblies despite calculating that there shouldn't be a risk. So based on these results and the fact that releasing it to the code means that it's going to be built by the worst possible trades with the worst possible materials, we couldn't really recommend it for widespread adoption. And you might push back saying, look, 50% relative humidity, that's crazy. More and more with tight construction and, potentially people turning off ventilation systems, we're seeing stuff creeping up into that level. So that actually is a real risk. If there was a place in the code for, dude, you effed up, you're getting mold on your sheathing, and you need something to fix what you have there, this is a fantastic solution, if you were backed into that corner, but there's nothing in the code that says that's the situation you're allowed to use it. So people say, like, can I build one of these roofs without spray foam? Yeah, absolutely. So, you can put instead of using rigid board foam over here, you can use mineral fiber, Gutex wood board. That's fantastic. If you want to do a completely safe all cellulose assembly, Chris Corson, you're in the audience. This is your image here. He monitored the heck out of this assembly. His results were boring and beautiful, just like low moisture contents throughout. So if you can't tell, it's a rafter frame, structural sheathing, TJI outriggers, vapor open membrane, and a batten cross batten system. So any moisture that gets through just whisks away. So are you calling it for time, Mike, or should I kind of just finish off 2 more slides?
Or yeah, finish up, Koda.
Okay, cool.
Yeah.
So like if you want to do these things, if you look at what we've seen so far and say, like, I think we can make this work, this is my recommendations on keeping things on the safer side. Keep the relative humidity low for the life of the building. Do a lot of testing to ensure the air tightness of the interior air vapor control layer. I'd recommend a variable perm vapor retarder. It gives you the most drying possible in a potentially marginal assembly. Use a big diffusion vent. Insure the pack, and I'd avoid lighter colored roofing, and also putting solar on that roof might increase risks, but I'm not sure by how much. So the one case where, I know that this should work quite well is doing this type of Cape Cod story and a half where you have this short slope section. And over here, you're dealing with that little channel where you're trying to stuff a ventilation chute up there. You don't have much cavity space to begin with, and you just end up with pretty much a half-ass solution. Based on, everything that we've seen in this research, doing this where the moisture has a chance to escape up into that vented attic, that's a pretty darn good solution in my opinion. We haven't proven it, but a lot of weatherization guys have done that for sure. And that is it, packed in. So
that was fast. Thank you very much. That was a lot of info.
Holy cow.
Quick question, Koda. Most of us hosts are in the Northeast. Travis is in Kansas City. We have other people around the country. Do I recall from the code that in warmer zones like 1 through 3, are vapor diffusion ports already in the code for those zones?
That's correct. So when we're talking about climate zones, I believe 1, 2, and 3, it is acceptable to do, insulation, fibrous insulation up at the roof line, diffusion vent. I believe it's 2018 I codes onwards. Might be 2021, but I think it's 2018.
I think it's in the 2018. And is that stuff you guys contributed to? Do you support that? Is that something you would not support? Is that coming for cold climates as well?
That came from Joe, so that's definitely from our shop. We're completely comfortable with zones 1, 2, and 3, for sure.
Okay, excellent.
Should I give control? Oh, go ahead.
Or no, just I have a bunch of questions, but one, I'll let some other people talk here too. But you didn't cover open cell foam. I know, especially in warmer climates, people like open cell foam. It's air impermeable, so it's technically allowed up here. But most people I know say don't use it in a roof up here. What's your stance on open? It's not fluffy, but because it performs sort of like fluffy. What's your take on open cell in an unvented roof?
You bet. So first, getting to the code question, it is code compliant. However, I believe in zone 5 and higher, it requires a class 2 or tighter vapor retarder applied directly to the underside of that spray foam. Basically, you can't leave the open cell just sitting by itself. Once again, yes, I know there are a bunch of open cell roofs out there, but yes, we've also seen failures. The other risk that we've seen in open cell is this whole thing. Let me just jump back to that, where it's called ping pong moisture, where basically during the day the sun comes out, the moisture gets blasted out of the sheathing, and then come night that sheathing becomes cold, the moisture gets sucked back in again. So what this ends up resulting in is what we call this moisture concentrating machine. And so how does this actually manifest? People go up into their attics with open cell and they go like, holy crap, it's crazy humid. And it's like 60, 70% humidity up in there. So what they've built is basically a moisture concentration machine with the sun, a solar powered moisture concentration machine causing that problem. So closed cell doesn't have it because of the vapor control aspects.
Okay, excellent. Any other hosts have questions? Should we turn it over to?
Well, we were going quick, Koda, and I think I missed when you were saying realizing that no air permeable insulation is ideal for an unvented assembly. Which of the not ideal options is the best? Is it cellulose? Is it dense packed fiberglass? Is it open cell foam?
Sorry, just to make sure I understand your question, is it basically if I'm not doing closed cell?
Correct.
Okay, yeah.
Which of the fluffy stuff basically is the best?
Well, I would say that open cell is the easiest lift in terms of getting it past your local building official in terms of, it's, here's all the paperwork and you'll have an easier time. If you're going with, fibrous insulation, instead of concentrating on material, the first question is installation, the density of the pack, tightness of the air and vapor retarder on the inside. That's priority 0. Then after that, I like cellulose a lot. I've done a bunch of these studies where, the whole, as Bill said, hydric storage and hydric buffering and the mold resistance from the borates, that saved it pretty well. It's, it's impressive stuff for sure.
There was some there were questions for Bill.
Oh, I have tons of questions.
Okay, yeah. I'll turn it over to you Justin, and for some crowd.
Well, we just Koda just reiterated again the need for proper density, and this is a big topic, obviously, from Bill. So Steve Demetric was curious, as a contractor in a state that doesn't have any experienced dense pack installers, how do you ensure that a cavity is properly dense packed? Is there a specific tool? Bill, you mentioned core sampling, but that didn't seem like it was at the time of installation quality control. That seemed like it was a post-mortem kind of thing. Is that correct?
That's correct. You could do it right after the installation, and we do that infrequently. But the best way is to, by knowing the cavity depth and the square footage of the area needing to be insulated, we go back to that dense pack chart I showed you. And, you know, the dense pack densities, you know, will typically fall between 3.5 and 4 pounds per cubic foot. The nice thing about dense packing behind fabric is you can actually press on the fabric and actually get a pretty good idea what the densities are. So a firm mattress is 3.5. When the cellulose starts feeling hard, it's at 4 pounds. And you know, you can, and by the bag coverage chart, and again, if you have a cavity depth of 18 inches or more, we recommend actually doing bag counts on each rafter bay to make sure that each rafter bay is up to density. So this way, if you keep track of the bags, you know the area of it and the depth, you can calculate, you know if you put the bags in. And if you didn't, it's as easy as, okay, well, I got to go back now and I got to retube it with the feed gate closed down a little bit more in order to build that density up at a higher level.
And Bill, is that the density that we find to be most successful, or is that the limitation of the machinery and the material being packed in there? You know, is it beneficial to go denser?
Yes. So with density, you have additional costs. Some of these big truck mounted machines, you could actually pack it in at 10 pounds per cubic foot. It would be literally hard as a rock at that point. We don't recommend that. I did a bunch of work when I was with National Fiber to figure out what these self-supporting densities were at these various cavity depths. And that's where that dense pack chart I showed up there, dense pack table came from. So if you got somebody who's conscientious, even if they didn't know how to do it, I'd like to have a conversation with them maybe before then. I'm happy to do that with folks. So we typically will pre-fill it with a big hose and then come back with a smaller hose. And some of the projects like that Canadian project they had difficulties with, they were trying to dense pack only with that large hose. And when you do that, the velocity of that large hose is not very great out of the end of it. And so therefore, you're only dense packing a very short distance from the end of that hose. So what we found is we want the speed of injecting it, dumping in insulation with that large hose, and then going back with the small hose, because with that 1.5 inch, 1.25 inch hose, now all of a sudden we're dense packing 12, 18 inches away from the end of the hose. So it's important to kind of understand a couple of these fundamental concepts when you're doing that.
And I didn't hear this question goes for both Bill and Koda. We didn't hear much talk, if any, about smart membranes. Is there any utility to those in these kind of assemblies for extra protection, or as just kind of a must-have? My idea behind the smart membranes is the one issue we get with them is they are air impermeable. So if we have isolated cavities where you don't have transmission between one bay and the other, sometimes it can help to fool the machine to thinking that it dense packs, because all of a sudden now you've pressurized that cavity, and when it gets pressurized to a certain amount, it's going to act almost like it's dense packing in there. Now, the way you're going to know is the bag count's going to be way off, and you'll feel the density will be really squishy behind that fabric. So the bag count and the blowing behind the fabrics are really quite, I think they're critical. If you want to make sure that you're never going to have a problem with your unvented roof assembly with dense pack, those are the two things you're going to use to make sure that everything's going to be okay. Okay. And Koda, you mentioned essentially, I can't remember exactly how you put it, but the exterior roof sheathing essentially being a zero perm surface. Is there anything to know about using plywood versus OSB and sheathing that deck?
Sure. Well, let me just finish off that last question on variable perm vapor retarders. So we did a comparison between, variable perm or smart vapor retarders. Those are the ones that open up when there's moisture behind them to allow some drying. We also compared them with a one perm fixed perm, which, totally meets code, and, saw how they behaved. One of the things from that research is when moisture collects inside that roof in the winter, it wants to get out in the summer, and we saw a little bit of condensation up towards the ridge with the one perm stuff, just didn't allow enough inward drying. Variable perm opened right up, no signs of any issues. So that's why, I made that, blanket generalization recommendation. That's what I would use for interior control. But getting back to plywood and OSB, plywood is a more generally durable product, in terms of it can take moisture and not suffer damage and not turn to oatmeal the same as OSB. That being said, OSB should be, you should consider OSB a family of materials rather than a material itself, just because the properties can vary all over the map. You can get, the cheapest commodity stuff, or you get, am I allowed to say trade names or not?
Sure.
Yeah, like, Advantech, Huber Zip, those are, pretty damn bomb-proof materials using, high MDI as their adhesive, so that's a world of difference between those. But in terms of allowing drying through the roof sheathing, once you put on the peel and stick or the asphalt shingles, the permeance doesn't matter anymore.
And can either of you comment on situations where you have a cathedral ceiling that leads up to a flat portion? Should that be done as dense packed and then loose fill on the flat portion up above? Is that the best approach for that, or is there some other way to skin that cat?
That's the best approach. And whenever we're not dense packing the insulation, we need to vent the area above that. So the upper part would need to be vented. And I agree.
Does that just mean exhaust vents, just ridge vents, or?
Code ventilation above that area. Yeah, I find that with cellulose, as long as we have a good air sealing going on, you need a connection to the outside. You don't need, to have necessarily, flow through ventilation on those attics.
Okay.
And I did want to just add, so if it's the choice between a set vapor retarder or a variable permeability vapor retarder, I would go with a variable permeability vapor retarder as well. So I think they do definitely have some advantages.
Yeah, I believe we have reps here from both ProClima and SIGA, so no, I don't think anybody's here from Certainty, but the performance numbers on SIGA and ProClima are pretty similar. They're, low class 2, I believe, when they're dry, and medium high class 2 when wet, or with SIGA it's directional, but those are reasonably good at keeping moisture out and they're airtight, so that's what you want.
We had a good question come in as you were talking, Mike, from Steve again. Recommendations about vent chute products to use that you can confidently trust to not collapse under dense pack.
Yeah, so that would be
is it AccuVent?
AccuVent Cathedral Vent is the best product. That corrugated, look of it means that the pressure is distributed and will not collapse. Now the problem with those products is they're plastic, so I'm not sure that you're ever going to get any moisture going through those into the vent, into the outside. That's the issue. There used to be a product that was made from fiberboard that actually allowed that to happen, but unfortunately that company is not around anymore.
Yeah, kind of analogous to that, a bunch of the Canadians, John Straub and company, did some research on various unvented attic assemblies, and one of the interesting bits is they did have the vent chute up in the cathedral ceiling, and what did they find? There was mold on the 2 strips, where there's no vent chute, and the part that was actually vented did work okay. So it's, you've built a chunk of unvented roof along with your vented roof in that case, so that's a potential risk.
Excellent.
Mike, I'm kind of curious to let Bill and Koda see if they have any questions for each other. It seems like we're kind of at opposite ends of this discussion here.
Well, go ahead.
Or just, this wasn't intentionally supposed to be a competitive thing. It's just as if we were all having beers at a bar together. So just what questions might you have for each other?
Yeah, I have a question about the install densities. Koda, did you folks do any density testing in there to figure out what the install density of the cellulose was?
Yeah, that's exactly the question that everybody asks in the audience. So on the winters 1 and 2, the ones where we saw the settling, we did not actually do density testing, putting cores in our roofs, but it was installed by an installer handpicked by the manufacturer who was asked to do this project. After the repack, they came in and rehosed everything, packed everything solid, and we were north of 4, I believe. I have the numbers in my report, but it's in that range.
Okay.
I also measured the density for the fiberglass, and it was pretty serious as well, between 2 and 3, I think.
So after it was repacked, remind me again, has the roof been opened up after that time?
Yeah, we opened up it from the inside, just dumped all the insulation, and the takeaway was the damage is all at the ridge. Those photos that I showed, that was the only damage that was actually in these assemblies. Once again, the top is where the action's at.
Yes, yeah. So we don't know on that second repack if the cellulose did separate from the roof sheathing.
Yeah, I can't say that for sure, but no evidence of it.
Okay.
And also for those who are, I don't know if folks were coming to this hoping like building science versus Bill Hulstrunk cage match or something, I think that we have Bill and I have this very similar observational points that when we're just interpreting them in different directions. I'm kind of looking at it from a researchy as well as what can we put into the code, especially because building codes are typically not allowed to be manufacturer specific. Like all these manufacturers are playing these games at the code hearing, say like, if we change the insulation value to R15, we can screw cellulose out of this game and that kind of thing. So, it has to be insulation material neutral as a result in the codes.
Right. Yeah. No. And there wasn't any advance warning here. So I think it's questions of like what meets code, what is reliably safe, what can be safe, what's definitely risky, what's definitely never ever do this. And so it's sort of on a scale. I mean obviously we would like to be able to do whatever we want and have it be code compliant, but sometimes we have to make decisions. Do we use spray foam or use cellulose and maybe a slightly risky assembly, or how do we make it less risky? And so one question Chris Corson asked earlier was, one way to make this kind of assembly safer is to add insulation on the exterior, like with his assembly or the ones you showed coded. Do you guys have the building code has sort of a prescribed ratio of interior to exterior, but have you guys done testing or studies to confirm, or do you have ratios of interior to exterior insulation you like to go with, or depending on climate zone, of course?
Yeah, so let me just share my screen once again, just so that I can, which one? There we go. Share. So this is just one of the articles on BSC's website. So if you look at the building code as it's written, it says, thou shalt put on R certain amount of, foam, spray foam, or rigid foam on top of your deck, and it varies by climate zone. The thing is, Joe originally wrote this as a ratio, given that's how the physics actually works. Fluffy stuff versus the rigid stuff, the ratio of that determines what the temperature is at the interface between that and what the risk is as a result. So unfortunately, when the code was written, his code advisor says like, no, we can't have people calculating ratios. That's crazy math. We can't have that in the code. It's like, seriously? Okay. So that's why we ended up with those, R5 and zone 2 kind of stuff. So the thing is, the actual ratios are calculated out. So in BSI 100, Joe talks all about this. And walls, roofs. So, you can see the table right there. Climate zones 1, 2, and 3, 10%. Zone 5 here in Massachusetts, 40%. Getting up to zone 6, 50%, those types of numbers. And that's the minimum foam versus compared to maximum, fluffy stuff.
And
Right.
and Bill and Koda, I believe, Koda, your research was limited to cellulose and fiberglass, right? And
Correct.
you're mostly a cellulose guy. Have either of you either played with the concepts of blown mineral wool or blown wood fiber insulation, if you're able to get your hands on such a thing? And if you haven't, do you expect there to be any difference that we might find in those other materials?
I don't. I mean, if the material is hygroscopic, which would be any wood-based or plant-based insulation material, I would imagine that they would be similar. The key, though, is when you talk to these manufacturers that manufacture these products, when you start to ask them about what the self-supporting densities are for the products, things get pretty weird. And I've seen some things that just don't make sense. They're either really high or really low sometimes, and I have a hard time being able to think that those numbers are realistic.
Yeah, I don't have any experience with blown mineral fiber. I would expect it would behave mostly similar to the blown fiberglass. One of the things that I have in the reams of reports that we've generated is just comparing the moisture storage between fiberglass versus mineral fiber versus cellulose. And cellulose is way off the charts. You can barely see the line of the fiberglass in comparison.
And
Yeah,
is there any difference?
Really thick wall assemblies, because that's the other thing that people are concerned about. And I have a lot more data on these big, thick, 12 to 18-inch wall assemblies. And I have looked at some fiberglass ones just because I've asked the question, okay, you guys are concerned about the cellulose. What is going on in a fiberglass wall? And when I've done the moisture testing in fiberglass walls, the fiberglass sheathing is always running higher moisture content than the big thick cellulose wall. A 2x6 fiberglass wall with a vapor barrier actually is running at a higher sheathing moisture content than a 12 to 18-inch cellulose wall without a vapor barrier. So yeah, so I mean, the other thing that sometimes drives me crazy is fiberglass and cellulose, they're completely different in terms of how they handle moisture. Fiberglass is hydrophobic, while cellulose is hygroscopic. So with fiberglass, the moisture just basically passes right through it as if it doesn't exist. And the cellulose, because of that hydric buffering that we talked about, is gonna operate a lot differently. And a lot of times, I mean, the other thing is when you take cellulose out of an assembly that's been there a long time, what you're typically going to find is the assembly is preserved really well. You're not going to see the staining. You're not going to see the things like that you see commonly with the fiberglass. And the same with these roof assemblies. If that cellulose is all the way up against that roof sheathing, when you take that cellulose out, it's going to look like it looked when it was installed. If there's a gap there, that's typically where you're going to see the mold or the moisture damage, where again, the moisture's gone through the cellulose, hit that air gap, gone through the air gap, condensed on the roof sheathing, and then that moisture is lingered long enough where now you're going to have some issues over time. And that's why no loose, fluffy cellulose and then unvented roof assembly, unless you want to have potential to have some problems with that.
Koda, anything to say back to that?
No, nothing, not much to add.
No, I have a sort of a burning question. Actually, probably the main reason I wanted to have you guys on was to get the information straight from the source. I end up dealing, not always by choice, with a lot of low slope roofs, and trying to do low embodied carbon projects. I really try not to use foam. Or if I do use foam, I try to use as little as I can. What is is there a safe way to do a low slope roof, say, less than a 2-pitch, with cellulose or fiberglass or mineral wool, or does it have to be spray foam, or does it have to have something else?
Well, I'm also a big fan of scissor trusses, where you can have that look of a cathedral ceiling on the inside, and then you can just loose fill whatever depth you want and ventilate above that. That's certainly would be one way of maybe accomplishing some of the same aesthetics of it, unless you're looking for that low slope on the outside. Anybody who's ever worked in a low slope roof will tell you they don't ever want to be in one again.
Can you guys briefly explain the worry about low slope on vented roofs? Mike?
Oh, well, it's with a low slope roof, so typically like a commercial roof or modern design with a membrane like EPDM or TPO membrane. There's usually, as I understand it, roof venting works from the stack effect. So you need a height difference in order to create a pressure differential at least part of the time. And when you get down to a low slope, which is like, anywhere from 1/4 inch per foot to 2 inches per foot, you don't have enough differential to create that stack effect. So a conventional ventilation strategy is not code compliant below a 2-pitch, but I know lots of builders who do it anyway. And it's one of those, if you don't see a failure in 10 years, is it still a failure? I don't know.
Yeah, I mean, over the years, we've done a lot of flat roofs as well. And again, in my mind, it's all about density. Make sure you got the density there. I do like Chris Corson's idea of using, a highly permeable membrane on the outside, and then strapping over the top to create an airspace, and then, building your roof system over the top of that. That's pretty bomb-proof. And at that point, does it matter if the cellulose density is correct? Probably not. I mean, the moisture is going to come up. It's going to go through that membrane into the airspace, and it's going to come out. So you can make these things definitely, I would think really foolproof with some extra materials in there to allow that.
Yeah. Anything to add to that, Koda?
Yeah, let me just see if I can share my screen. Give me 1 second. I just pulled up something relevant. Share. Yeah, so Martin Holliday actually did exactly a discussion on this. Everybody can see that all right?
Yes.
Yeah, so I think we've hashed through why a low slope roof is so risky. There's no driving force from low to high. That being said, if you do something that log in, I'm a frickin' member. Come on, guys.
And you should be too, everyone.
Here, here. Yeah, so if you basically have a nice clear vent space over the fluffy stuff, and you have a little bit of height going on, like we're talking, this is the sketch that we've put together with, a cupola, so there's actually a low to high difference using that, stack effect, warm air rising. That's a pretty safe roof at that point. I'd still want to make sure that my air barrier, the ceiling was pretty good just from energy and also for moisture, but this is a workable solution. Whether or not you have the space is the other issue. The other way to do this, of course, is with, instead of using rigid foam on the top side, you could do it with mineral fiber. High density mineral fiber boards are pretty much an off-the-shelf solution now, but it's still not a wood-based material.
No, thanks. Well, that I believe I could be wrong. I spent a lot of time reading the code, but I forget things. I believe the way the letter of the code is written is that the exterior insulation is supposed to be impermeable, but is the intent that it can be that it can be a permeable insulation on the exterior as long as you're controlling the R value. That's the main issue.
Yeah, the biggest thing is having this bomb-proof continuous air barrier between those two.
Okay, that's good to know.
I have a burning question for Bill about the dedusted cellulose. Same. Can you enlighten us?
So typically what happens when they manufacture cellulose insulation is you have a dust collection system. Anytime you have a cyclone, you have to be pulling off some air and you're removing dust at that point. But because the fire retardants that have historically been used in cellulose, they're so expensive that what they do is they actually end up just introducing that dust back into the product because they don't want to lose the fire retardants. NatureTech has developed basically a different novel fire retardant, I'll call it, which allows us to basically dedust the material and not then add that back into the cellulose. I've never been up in an attic where I've been blowing something and thought, man, I wish this cellulose were dustier. So this came from, you know, actually I was developing a system working for another company. At the time, this NatureTech approached me, and we were both looking to do the exact same thing, and they actually had the patent on their dedusting technology, which was the same system I was working on. So because of that, I felt that, you know, a dedusted product with NatureTech is going to be the way to go. So we're still working through some other issues. The plant will be up and running sometime this year, hopefully sooner than later, and we'll get this out on the market. The people that have seen it have just been absolutely amazed and astounded by their ability to see where they're blowing the cellulose. This is the other thing. You're up in an attic blowing it, and a lot of times you're blowing into a cloud. You can't see it. You got to move your hose out of the way to see what the depth is doing and then move it back. This way you can actually blow it and see exactly where it's going. It allows you to get a more consistent, you know, even level up there, and then less cleanup because that dust then is traveling, you know, places where you don't want to.
Question somebody else asked, and this is an assembly I've done as well. When you're doing an unvented assembly, you know, there are the variable permeance membranes. What do you think about dense packing between, if you say you have zip sheathing on the exterior and you use zip sheathing as your interior, are there, from a building science point of view or an installation point of view, are there, well, I guess it would, so do that and then overvent the roof. So basically you have a zip cellulose, zip, or any insulation in the middle with zip on the exterior. Then you strap the exterior and do metal roofing. So it's ventilated. Moisture can get through the zip and vent underneath the roof sheathing. I mean, vent on the outside of the roof sheathing. Sorry, that was not clear at all. But did you guys follow what I was trying to say?
You lost me.
Okay, so so you build a normal roof, you know, rafters with zip on the exterior. On the interior, instead of Intello or Sega, you put more zip sheathing. So you have a zip sandwich. And then to complicate it, to call it a vented roof on the exterior, do cross strapping or diagonal strapping, and then a metal roof on the outside of that. So there is a vent space, but any moisture has to get through two layers. If it's coming from the interior, the moisture has to get through two layers of zip to get to that vent space. Does that sound like a risky assembly, like still too confusing?
No. So down in Connecticut, there's a builder down there who did a passive house, and he has zip on the outside. It's a 18-inch dense pack cavity, and then he has plywood on the inside with then sheetrock on underneath that. And we've been, for a passive house, we had to do, I think it was 3 years of moisture testing on that roof assembly just to show that there weren't going to be any problems. And that roof has been just really, really stable. It doesn't have quite zip on the inside, but it does have plywood, basically, you know, a rigid insulation or rigid board on, you know, both sides of that assembly.
Okay.
Yeah, if I built that, I would consider, instead of using zip on the middle, the outermost layer, I'd consider maybe plywood with a vapor permeable, you know, type of sheathing. Water control membrane, just because, you know, having that much more outward drying would be a plus for sure.
Mm-hmm.
You know, if you look at the permeance curves of OSB versus plywood opens up like crazy when it gets wet.
Okay, and with the metal roofing, there could be some condensation from night sky radiative cooling, so you could get some dripping, and probably better to rely on a good separate WRB rather than zip, or do you think the zip would stand up to night sky dripping?
I have no issues with zip as a water control layer, so that's not my objection here. It's just the tweaking the permeance of this sandwich layup is more what I was talking about.
Okay, thank you. Yeah, any other audience questions? Any other?
No, that was most of it. Steve did weigh in with a while back in the conversation. Is there any tool that you can use to measure Hydric? I believe it was Hydric capacity is what he was asking about.
It wasn't just density.
Well, let me go back now.
Oh, well, another question I saw from Matt, and this is 10 years ago, I built a couple of houses with unvented dense pack roofs with power packs, so reinforced poly on the interior. So, you know, and this was in Zone 6, coastal Maine, you know, reasonably well done, but certainly not, you know, I didn't know what I didn't know back then. So how much it was at a different company. I'm not going to get sued. So how much should I stay awake at night worrying about this?
Yeah, so I know some of the power pack installers, two of them at least in Maine, and I thought both those guys had a pretty good understanding of density. You know, a single point moisture test into that cellulose in the spring is going to tell you whether there's any issues there. Again, it's been 10 years. You haven't seen any issues with it. It's probably fine. And again, those two installers that I knew that were working in Maine with PowerPack, both seem to have some pretty high density installations.
Yeah, you know, this was one of those, I'm sure. So yeah, as well as could be done. I'm sure nobody's gone in those attics since they were built. So unless the roof shingles actually fall through, nobody's going to know if there's a problem. But just
Mike, I'm going to request special permission to promote Steve Demetric, who has a question about layers of paint and how they might affect something with a smart membrane.
I don't know, Steve. I don't know. Yeah, sure.
He has the most questions of everyone, and I don't understand how he's wording these questions, so I figured I'd just let him ask it himself.
Come on in, Steve.
Steve, you are about to be a panelist. Welcome. Let's hope he's wearing pants. Can you hear us, Steve?
Can you hear me?
Yep.
Yeah.
Okay. Yeah. So I had a really specific question because we're trying to use a lot of dense packed cellulose more and more. And the first passive house I built probably 5 years ago now, we had a massive leak because the homeowner left the hose bib on. They left their hose attached to the hose bib all year long, and the frost-free valve wasn't frost-free anymore. And so it was couple layers. It was like 4 inches of closed cell foam, probably 8 inches of dense pack fiberglass, sheetrock, blue board, plaster, paint. And one thing I noticed was the amount of moisture in the wall. It actually was bubbling the paint off before like within a day. It was all, the back of the sheetrock was moldy, the paint was bubbling off. And ever since then, I always wondered, we put all these smart vapor retarders into our wall assemblies, but how do we manage all of those multiple layers of paint on the inside of the wall? Because the permeating of all those paints, when you start adding 3 or 4 layers of paint on, if it's a dark color, it might be 4 coats of paint over 2 coats of primer. How does that affect the smart vapor retarder that we're worried about?
Yeah, sure. I can go ahead and field that one. So let's just kind of talk through the problem. The first half, of course, is the wintertime problem in terms of moisture going into the wall. Adding more layers, of course, decreases the permeance. So in general, that's safer. So we're talking about the case of summertime drying, or, you know, a lot of bulk water leak inside the wall. Can that moisture get out? Class 3 latex paint, 10 perms, you know, that's a boatload drying. It might be a limiting factor compared to the super vapor open variable perm retarders. But one thing to remember is it's not just like a one-dimensional stacked woofy assembly most of the time. It's, you know, gets through that membrane, there's a little gap in there, you know, and soaks into the, you know, can hit the drywall, travel laterally. There are all these different pathways. So, what I would expect is if you had something super low perm, like, chucked a mirror or a painting, with a glass frame in front of a chunk of the wall, that might be a spot where you see a problem if you have a massive amount of moisture blowing through, but that's pretty much an edge case to me. I don't see it being practically a huge effect.
Well, actually, the situation I had wasn't. I realized it was an isolated situation, but when I look at long-term moisture buildup in assemblies, so if you have a zip roof on the exterior that's taped, that's totally air impermeable, and you've got, which is probably about a perm of 2 maybe in a zip sheathing when you're looking at it, and then you've got dense packed cellulose, a smart vapor retarder, and then you've got 4 layers of paint on the inside, which when you start layering those paints, maybe 1 layer is 10, but when you start 4 layers is not a perm of 10 anymore. I would think that the perm layers would actually stack upon themselves, and now you'd be a significantly lower perm. So that's where that's where it starts making me project, like, what's actually going to happen in some of these roofs.
Yeah. So just to clarify, the 10 perm-ish number is roughly, I believe, primer plus either 1 or 2 coats of latex paint. So that's already more than 1. If you're talking about 4 redoing primer plus paint, that drops it to about 2.5. So, it still, does cut the drying. It's less than what you would get out of the variable perm membrane itself, but it's not cutting it to like a class 2 vapor retarder.
All right, Steve, you've been demoted.
Thank you.
Koda, Ben had a quick question. I saw you do this talk at Nessie where you had an hour and a half and it was still tight. So to ask you to do it in 10 minutes is ridiculous. But Ben's question is, on the vapor diffusion vents, vapor diffusion ports, is 200 perm, is that required? What's your limit? What's the range of the perm rating?
Yeah, so great question. One of the things that we did that experiment with is, how low, what do we need for this permeance for that diffusion ridge vent? So we tried out as a comparison using Tyvek commercial wrap. That's about 50 perms. And the takeaway was like, yeah, that doesn't work really. So, 50 perms was not enough. Those are the 2 data points that I have. So good, bad is about it. So I would stick with, the fancy brown membrane myself or something in that range.
All right, and that was a Delta Dorkin membrane, I think?
Correct.
Yeah.
Dorkin Delta Fox. Okay.
Thank you. We're coming up on our 7:30 time. Are there any before we stop? We just want you guys to leave everybody with a few words of wisdom. But are there any other questions?
That was it, Mike.
Okay, yeah. So any words of wisdom here to leave people with if they want to do fluffy installation in an unvented roof? What's your takeaway?
Don't do it.
Don't do it.
Dense or vent.
All right.
Yeah, I had my laundry list of, air tightness, density, but, if you have an option of doing a vented roof, that's a fantastic assembly.
Excellent. So vent when you can. All right. Well, thank you very much, guys, for all your time and expertise, and thank you to the audience and other hosts. This was a lot of fun. I hope you come back and join us in the audience sometime.
Cheers.
Yeah.
All right.
Okay.
Thanks, everybody.
Thanks, everyone.
Thanks a lot.
See you next week.
Thanks for joining us. Christine said hi, Koda.
Oh,
I talked
okay.
to her earlier today. She also
Awesome.
told me to read one of the building science things every single day. She's like, you can start at the beginning, read one every day, and then start again, and you'll learn something new every time. So she says when she asks Joe something, he's like, well, go to this one and read it instead of telling her the answer.
Absolutely. I do that to my clients too.
Yeah, those are great. I tell that to people all the time. Start here, read these things. Get the Cold Climate book out. I hear you're putting together a new book. No.
Joe probably is. I'm, like a lot of the time, the way that information travels within Building Science Corporation, think of those nature documentaries with the shark feeding frenzy, and they're all like swooping through the fish, and those little down. That's us down here. So.
That's awesome. Are you speaking at Nessie this year?
Yes, I'm gonna do the long version of this talk at Nessie, and I'm looking forward to seeing everybody at the conference.
Yeah.
Excellent. Yeah, that's mid-August now.
Yep.
We'll see.
Maybe.
Yeah.
We're talking about making the Fine Home Building Summit a digital event somehow. But I mean, at this point, we don't need to make a decision for October, but we certainly need to be prepared with alternatives should it come to that.
Yeah. No, they just closed most of our state fairs that are August and September. I think a lot of those just closed.
Yeah.
Strange times.
Well,
all right.
This has been one of my favorite ones. You guys are awesome.
Yes.
Yeah.
Likewise.
Thank you.
Thank you very much. Have a good night.
Appreciate you being on.
Okay. Take care.
Yeah.